so based off of, we said a logarithm is an exponent, then we should be able to solve logarithmic equations. So if I get me a little purple, if I get me a color going on here, then what I'm basically saying is 3, remember, is my base. This, a logarithm is an exponent, would equal this value. So in other words, 3 raised to the second power equals 4x minus 7. So now we have something we can solve. 9, 4x minus 7. Add 7 to both sides. We get 16 equals 4x. Divide both sides by 4. And we get x equals 4. Now, if you're a good student, not a lazy student like me, you would check this. So log base 3 of 4 times we just found. The answer was 4. So log base 3 of 16 minus 7. So log base 3 of 9. This says, what would you raise 3 to get 9? Oh, well, looky. Worked out perfect. Okay, so let's try another one. So now in this case, we're given our base is x. So this says x raised to my exponent equals 64. Now technically, when you square root the square to get rid of the square, you're supposed to be doing plus and minus. However, we know that logarithms, the bases must be positive. And so we can get the square root of 64, which is just simply 8. And definitely you can see 8 squared would give me 64. If I have these one, so e to the 2x equals 5. So now notice I'm kind of going backwards back to exponentials. Well, remember that if e to the y equals x, then y equals ln of x. Remember this, our e in logarithms, base e was ln. So in other words, what this is saying is that typically what we say is we take ln of both sides. So ln. And notice looking over here, what's going to happen is I'm going to end up with just 2x equals ln of 5. Okay, so based on my definition, and if I solve this for x, I would divide by 2, and if I throw that in a calculator, I get something like 0.805. But it's this definition over here that's important to recognize. What's happening is when I do ln of e, it kind of cancels out the e, and then you bring the 2x down. All right, if I want to use logs to solve this one, so certainly what you always do is you look at your base, and I can see that my base e is going to be ln. You typically want to get your base by itself. So I could divide off 4. And again, anytime that I want to undo or bring down my exponent, I do whatever the base, in this case, base e, which would be ln. So I take ln of both sides, and that gives me x plus 1 equals ln of 5 over 4. And then, of course, I can subtract 1. And for an exact value, that would be your answer. If we look at an application, blood alcohol concentration is the measure of alcohol, in a person's bloodstream. So a BAC of 0.04% means that a person has 4 parts of alcohol per 10,000 parts in the body. And then down here says the blood alcohol concentration for all states to be DWI. And 1 drink, this just gives you kind of an idea here based on your weight and the number of drinks, what your blood alcohol content would be. So don't you do it. So relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. If an individual with a blood alcohol content of 0.02% is 1.4 times as likely to have a car accident as an individual that has not been drinking, then the relative risk would be this zero of the blood alcohol content would be 0.02%, would be the 1.4. So 1.4 times more likely. So they give you this formula, and it says recent medical research suggests that the relative risk of having an accident while driving a car can be modeled by this equation. So right away you can see it's an exponential equation where X here is the percent of concentration of alcohol, and then K is just some constant. So if I want to find the constant then, so I'm looking for K. Let me make sure I got my pencil going here. And so I have my formula equation, R equals e to the kx. I just simply plug in everything that I know. My relative risk, 1.4. Okay, equals e to the k, the percentage, 0.02. And it is put as a percentage. Okay, so you don't change that to decimal. That does mean percent. And as we've been doing, how do you solve with the base e? Natural log. So I take natural log of both sides, and we could go ahead and turn that around because that's how we typically like to write it. And then of course I get 1.4 equals 0.02k. Divide the 0.02 on both sides. And I want to put this in my calculator because I'm going to use this value. So I get 16.82. So that's going to be my constant. If now using this information, I want to find relative risk. So once again, I have my e to the kx. Then my relative risk would be the 16.82 that I just found. And based on my percentage, and I get about 17.5, which means a person is 17.5 times as likely to have a car accident with somebody with no alcohol in their system. Using the same value of K, what blood alcohol content corresponds to a relative risk of 100. So I set my R to 100. 16.82x, and of course I'm solving for x. ln of both sides, which will give me, bring this down, and then of course divide by 16.82, 16.82, and I get about 0.27. So as you can see, we use the logarithms, exponentials as inverses of each other to be able to solve depending on one or the other. If the law asserts that anyone with a relative risk of 5 or more should not have driving privileges, what would the concentration of alcohol in the bloodstream should a driver be arrested and charged with DWI? So once again, my relative risk being 5, still using the same constant. And then, as you can see, I'm going to go through the same steps. ln of 5, 16.82, and I get the blood alcohol content of 0.96. And that ends logarithmic functions. So we'll move on to properties and then get even into more applications.